Okay, thank you. What I'd like to do today is talk a little bit about my perspective as a continental shelf oceanographer and where I perceive that our community is going to be interested in these things or not. So,
Because I started recording, then it's try it again.
Go the other direction.
Oh, okay, I got it. Okay. So here's a list of topics, not inclusive, of course, but that people who identify as coastal oceanographers will usually be working on. Things like coastal upwelling, which is very important for biological productivity over the shelf. Tides and related effects, mixing and so forth. Wind-driven currents and coastal trapped waves kind of go hand in hand. It's kind of hard to separate the two topics. Estuarine outflows are extremely important, and we see some wonderful examples here on the East Coast. Inner shelf processes, and inner shelf, I mean water shallower than maybe about 30 meters, where mixing and dissipation is important throughout the entire water column. And the shallower the water becomes, the less important Earth's rotation becomes. So you get into water that's shallow enough, and forcing due to incoming surface waves dominates what's going on. Instabilities at fronts. There are all kinds of fronts in the coastal ocean. There are tidal mixing fronts, there are upwelling fronts, and on. There are estuarine boundaries fronts, most of which appear to be unstable in nature. And that's something that's been a fairly popular topic in the last 10 years or so. Response to oceanic variability. I'll give examples of that in a minute, but that's something people are certainly concerned about. Effect on the deep ocean, you see that in parentheses. Most of the people I can think of who identify themselves as coastal oceanographers are concerned about what the deep ocean is doing to us, and not so much about what we're doing to the deep ocean. But that's really an important topic, and I'll come back to that later on. So out of all those topics, how many of these actually have an important piece in the slope? And there are some. You know, the inner shelf obviously is not going to be relevant. But one example is upwelled water. This is temperature. Oops, didn't want to do that. A temperature image of the west coast of the United States. There's San Francisco Bay, Monterey Bay. And this is during the upwelling season. In the summertime, you have cold water near shore, high in nutrients, so it's high in phytoplankton population. But what's interesting in this perspective is that as the water goes offshore, it tends to form up into these narrow, relatively narrow filaments that can be quite pronounced and can be there for weeks at a time in some cases. Energetic currents shooting out these things in about a knot. So they're impressive features. They extend across the slope out into the deep ocean. So that's certainly something over the slope that people who are studying about upwelling are really interested in. Forcing of tides. Tides over the continental shelf. The astronomical forcing is not very important, but what is important is how the tidal currents over the shelf respond to what's going on offshore. And offshore means over the slope and beyond. So you bet the slope's important for that. Oceanic variability. This is an example that's kind of close to home. Here we are in Narragansett Bay, Long Island. And here's the shelf break here. And this is a typical kind of image. There's the Gulf Stream coming along here. And as the Gulf Stream goes along, it meanders and breaks off these eddies called warm core rings that bang up against the edge of the shelf, and they don't get onto the shelf. Because one of the important things to think about here is that flow on a rotating planet, if it's relatively low frequency, meaning time scales longer than 5 or 10 days, just flat out doesn't want to cross isobaths. And so here we are, these things go up against the shelf edge and they they don't get on, but we still suspect that they play a role in terms of materials exchange across the shelf edge. And for sure, if you look carefully at these things, they very often have these streamers of shelf water coming offshore, maybe only 5 or 10 kilometers wide, but very energetic, and they seem to play an important role in the exchange of materials across the shelf edge. So there's certainly a slope process that you care about. And then the effect in terms of what shelf processes on the deep ocean. A lot of these things aren't priorities for a lot of shelf oceanographers, but you bet they're important. And a really obvious example is the formation of dense water over the continental shelf in the wintertime tends to dribble over the shelf edge in the form of trains of little eddies, 5-10 kilometers across. And that's important for the global ocean circulation, the bottom water that forms off Antarctica and so on. Or if you're off the west coast of the United States, very low frequency coastal trapped waves, meaning periods 50 or 100 days, will drive motion in the water farther offshore, Rossby waves or eddies and things like that. So there certainly are shelf effects on the offshore. But before we dig into this anymore, I want to set in your minds one simple idea is if you have conservative flow in an ocean, conservative meaning that dissipation is not very important. So that's most of the water column.
All right. It's just
You
you.
come up with a scaling by scaling the vorticity equation, which basically says that the vertical scale of any given feature
Maybe
is
my wife come
proportional
down
to the
too.
horizontal scale of that feature. And
Thank
the
you, my never-
proportionality constant is set by F,
That
which
job
is
offer.
the reverse
'Cause I
rotation.
really want to go to Mars.
N, which is
Assuming
a
I
matter of
bring my wife.
the
She
measure
hardly
of the
takes a minute from
stratification of the water
here.
column. So what that means in practical terms around here is that this
Look at-
latitude
no.
and the stratification you see out around warm core rings
But look,
is that if you have a feature that's 10 kilometers wide, it's probably not going to penetrate more than a couple hundred meters down into the water column.
You bet I do.
So the bottom line is that small features just don't penetrate to great depth in the ocean. So where's that take us? So in those processes that I talked about before, the fate of upwelling water, those cold filaments are small enough and narrow enough that you would never ever expect to see them to show up in bottom pressure over the continental slope. So we'll cross those out.
Question, it's like,
Please.
that's like the bottom pressure reporter measures like the whole water column, and it's like,
Yeah.
does it need to penetrate to the greater water depth?
Yeah, what happens, yeah, that's a good question. What happens is that these filament features have an expression in sea surface height, say, but as you go farther down in the water column, the density adjusts to compensate for that. So that if you get down farther, there is no horizontal pressure gradient associated with these things. So one thing to keep in mind about flows in the ocean is almost invariably a current is associated with a pressure gradient, the way Randy explained this morning. So that if the current goes away, the pressure gradient goes away. The pressure signal goes away. Does that make sense? Okay. Okay, so where were we? Okay, we've got that one. Forcing of tides. You know, that's still important. You would still expect to see a nice tidal signal in bottom pressure over the slope. But if you're a coastal person and you just want to know about what the tides are or whatever over the shelf, there are other things that are available readily, like really good models, that dynamical models that assimilate real altimetry tides, and to give you a really excellent product that tells you what the tides in the outer part of the shelf or in the slope are. Now, maybe you would disagree with me about the excellence of these models. I don't think so, but so you know, there's if you're really just interested in tides on the shelf, it's not obvious to me that these bottom pressure measurements are going to be of primary interest. clearly they're gonna, if you could assimilate them, they're gonna improve your models. But still, okay, so that one maybe not so hot. Response to the oceanic variability, yeah, for sure. Assuming that we're looking now at things that have horizontal scales of substantially greater than 10 kilometers. So those warm core rings I was showing you before do show up in bottom pressure. So that's something that is still useful. Cascading, these small eddies that dribble off the shelf, they're going to have small horizontal scales, which is going to cause nightmares for Randy's objective analysis. And because they have small horizontal scales, trust me, it means they have small pressure signals for a given velocity amplitude. Bottom pressure is probably not a great way to get at these things. But if you have temperature sensors on your bottom pressure housing, then that could be useful. So, okay, and then, okay, right. So bottom line, we're not going to see the small scale stuff in bottom pressure. So what I've just said, skip that. Okay, now here's another scale thing. This is now, let's talk about what we know about the scale of things, the ability of structures to get across isobaths. We'll call that cross isobath. We'll call that cross isobath scale LX. And depending on your assumptions, if you assume it's a time-dependent flow, you get a scale like that. If it's a steady frictional flow, you get a scale like that. You ignore stratification for now. But the important thing is that no matter which way you do it, some of these factors are the same. Y, capital Y, is the alongshore scale of whatever it is you're looking at. So the larger the alongshore scale of your feature, the more likely it is to be able to cross isobaths. And the F alpha down here, F is Earth's rotation rate, alpha is the bottom slope. And you can't do much about that observationally. The slope is steep, and F is substantial, most of the places we're interested in. So what this says is that you expect that most of these things going on over the slope that manage to get onto the shelf are probably going to have large long isobath scales. Yeah.
I don't see a stratification in that.
No, I left it out, and the reasoning being the papers I can think of that where they actually included it, like there's a nice one by John Huffnitz, came out qualitatively with about the same results. Now, John's study made some assumptions, and so you know the book is still open on this one. But you know, the results I know that do include stratification don't lead to a radical change in this regard. Yeah, I could preach for a half hour about that if you let me off the hook on. Okay, right. So again, you expect that it's only going to be the largest scale oceanic features that are going to get over onto the shelf. And that, yeah, there are more places you can say, yeah, but about that, but that's what you expect. And indeed, this, if you go way back, Gabe Shinati referred to this as, the insulating effect of the continental slope. And that's a good way to phrase it. Okay. So an example of what's left. Here's some the results from a paper by Hong et al. And basically what they did was they used a simple model of the oceanic flow driven by wind fluctuations. The time scale here is about 30 years. This is a Hubwheeler diagram at 18 degrees north. And so here's longitude across the ocean. And so the wind fluctuations are causing amplitudes of the surface height of about 10 centimeters of water. And they do this clever theory, and the result of the theory is they take these results and they show how it affects what's going on the shore. So here's a tide level, sea level records from Lewis, Delaware, at the mouth of near the mouth of the Delaware Bay. The dashed line is observations, and the solid line is the results of this model. So here's an example that frankly I don't think was as well understood as it ought to be, but where you have something going on in the deep ocean that's having a strong effect over the shelf. So there are the point is there are examples where we think this is important. And just to wrap up, who knows what else? The continental slope appears to act like a natural filter, that there's certain classes of motion that are just not going to be there. And so the opportunity we have here is to figure out how to exploit that natural filter. And, you know, there are things you can do, like start looking at radiation of eddies and Rossby waves from the west coast of the United States. You might be able to find a way to isolate barotropic Kelvin waves, things like that. And I know that we'll hear more in the next talk about how this can go to really good use. But the one parting thought I would have is, based on my understanding of these things, that if the greatest value to the shelf oceanographers would be if you put out arrays of bottom pressure sensors that cover large distances along shore. They don't have to be closely spaced, but if you had 3 bottom pressure sensors, each separated by 1,000 kilometers, any signal you find that's coherent among those 3 is obviously a large scale signal. And you could then use that to look at what's getting onto the shelf. Questions or comments?